continuing on with jobs. So the iJob parallel 4 transform, and I'm going to introduce this with the n-body problem that we dealt with, because it's a good example for this. Now, the sequential version of the n-body problem, and this is for a central manager, by the way, is that at each time step, delta t, dt, from the positions, we calculate the force on each one due to each other. So there are n of these, and each one is doing n force assessments. So this is an order n squared calculation, the calculation of a force. We then use the force to update all the velocities. We use our little v equal v plus dt f over m. And then I use those velocities to update all the positions. Position is position plus velocity times delta t. And this looks like it can be nicely broken up into 3 jobs: a force job, a velocity job, and a position job. So here's the sequential function that I used with the force. As input, I had the positions. I looped over an index that went from 0 to the number of objects. I got my position of the one that I'm calculating the force for. I set force to 0. I formed the distance cubed here, calculated my force, and that's due to the heavy star. But here's the loop on all the other objects where I'm calculating the force on them. There's this little trick here to have a heavy star. So let's convert this to an iJob. So this is an iJob parallel 4, just like we talked about. I'm not modifying the positions, so they can be a read-only public array. Forces is what I want to return, so it's not a read-only. And then I have delta time, the GM constant that appears, the object count, and my execute over index, where the rest of this is just pretty much exactly what I had in the sequential version, and the force index is stored here and returned. So the job analog to the velocity is pretty simple. I have a native array of velocities, which I am going to be modifying. This is also an input since we're updating velocities, v equal v plus. But the forces can be a read-only since I already calculated it, and it's in the previous one, and I do need the delta t. And again, the execute with the counter here is I. And finally, the position update. And here I'm using Verlet's rather than Euler Chroma above, but that's because Verlet is really good at conserving energy. And this demonstrates the iJob parallel 4 transform, there should be an S in there, feature that allows for direct access to an array of transforms. So this is pretty cool because it lets us directly manipulate transforms. And I'll set that up in a minute. So here we have we're updating, we're changing the positions, again with a P equal P plus velocity delta time, and this and the forces. But velocities and forces are both potentially read-only, and the other variable we have is delta time. So these 3 are pretty simple. Scheduling can occur in 2 places. One in the update function, if we happen to be using the internal time.delta time for the delta time. I don't recommend this, as these physics simulations often need much smaller delta times than what we have in Unity. In which case I would put it in the fixed update function. where I would specify a delta time of 0.001 or something like that. And I'm going to put these all in a set up all jobs function that I can call from either one, depending what I want. And notice the dependencies. The velocity job depends on the force job. It can't calculate velocities and change of velocities until I know the forces, and I can't calculate positions until I know the velocities. So there are dependencies here. So setting up all the jobs, I have my force job, I have my delta T, my positions, my forces, my constant GM, and my object count. And I have a handle for this, and I schedule it with object count, and in this case, a 64 here. My velocity job takes the delta T, the velocities, and the forces. Its handle now on its schedule depends on the M force handle, so this won't start until this one is completed. Note also that the force is order n squared, whereas both of these are order n, so they're pretty quick relative to this one. The position job takes positions, velocities, and forces, updating positions, and a delta t, and it depends on the velocity handle. So it also won't start until the velocity job has finished. And here's this transform access array that inside the position handle let us directly manipulate transforms. We did this right here. We have the transform access transform. That's the thing that we're passing in as a transform. And here I'm just updating its position. We can update position, rotation, scale, any of the transform components here. It's really pretty cool. So that's the scheduling, the setup of all of this. So we set up the native arrays the same way we did. They're vector 3 arrays for position, force, and velocity. My transform access array is transform access array. I have all these variables for the various handles. In start, I set my positions. I'm going to use allocator persistent for these because these might be big jobs that take a while, take more than 4 frames to execute. A bunch of magic in here. I'll let you look at the program for how to instantiate and set up the initial velocities of all of these things. And then looping over all these objects that I've made, setting their positions, their initial velocities, all of which was done in some magic, setting all the forces to 0, catching into M transforms, the object transforms, and in case I wanted to play with color, I'm also catching copies of their renderers. And in fact, I'm setting them to random colors. As I establish these native arrays, I also have to establish the M transform access array as a new transform access array with M transforms here that contains references to all of our object transforms. Now, one more thing, there's something called the burst compiler, which you have to include as a package. And I don't know if you've seen packages yet, but the package manager lets us look at all of the different packages that have been included in the project. These are the packages that I have in the project. We can also see the built-in packages. These are various packages that do things like physics and particle system, cloth, audio. All of these things are built in, but they're included here in the package manager. The registry shows all of the packages that are available in Unity. So there are a whole bunch of them here. And this shows the ones that we've included. Burst has been included. And there are many different versions of these that are available. I'm using the current latest here for Burst, but there are versions going back to version 1.1. Documentation for any of these is available here. So this is the package manager, and they have to be added at some point. Well, the Burst does. The amazing thing about the Burst compiler is that without doing any work whatsoever, and anything more than adding the Burst compile directive, this reduced the runtime of the force job, which is the order n squared part of the calculation, from 8.6 to 0.47, a factor of about 20 improvement. So I mentioned the packages, the built-in packages, the in-project, and the all packages. Packages are included from the manifest JSON. It's in the package folder of your game project. They look like this with various dependencies, a whole slug of automatically included modules. And sometimes if you can't locate the package you want, or if it's not in the list of available ones, sometimes you can add this by editing it manually, but I don't recommend it. So let's look back. Let me run this now, the end body here. And I've got the profiler up here so that I can see the behavior of this. And I start off with a sequential 400 particles. And you notice this is kind of pinned the meter. I'm only getting 8 to 10 frames per second here. So the rendering or the script usage is off the top. If I include rendering, I won't see that until I go to a faster job. Down here, we see the main thread, and I believe I can click here and press A, and it kind of scales this thing up. And I can see here's this fixed update that is my force job that's taking the bulk of the time in the player loop, which is taking quite some time. So, and down here are the job worker threads, which, because I'm not running a job, I'm doing it sequentially, are pretty much idle. They do get used for some little stuff, but not much happens with them. So watch now as I go to the job system. First of all, the scripting overhead goes to almost nothing. The threads are now busy doing all kinds of stuff. Here they're and doing it in parallel. Just to show you how much of the overhead is due to the rendering, I can turn on and off the rendering and see how much is due to rendering. And here's what happens when I go to the Burst compiler. The scripting load goes down again by a tremendous amount. My threads are now not so busy. Actually, the Burst with only 400 doesn't actually gain much in terms of the frame rate, since most of the cost now is in the rendering. But if I go to a parallel with 1000, now my script is, my overhead's back up to 8 to 10, even in the parallel case. But if I go to a Burst 1000, it goes way, way down. And I'm now getting a frame rate well over the 60 that is the nominal VSync. Throttling, which I have turned off here so that I can see these. So an awful lot of performance here when we switch from just an iJob to an iJob with the Burst compiler. And all of this contrasts with the sequential version that's just off the chart and barely able to do anything with 400 particles, 400 planets. So all very cool. And just to show you that I can, here's uh, a version of this. I've got my sequential that's running at 8 to 10 frames with 400. Here's the job with no burst that's now running at 40 or 50 frames with 400. Here's the job with a burst at 400. It doesn't speed up very much. The burst doesn't really get into its own until we go up to like 1,000. And now I'm getting 1,000 with 70 some frames. And I can go on to 2,000. And I'm still getting 40 or 50 frames per second. 3,000. And it's only when I go to 4,000 that even this throttles down. So I'm getting about the same performance here, 8 to 10 frames per second with 4,000 particles. That was about what I got with 400 run sequentially. So this is a very cool tool and definitely worth investing the effort in it if you're going to do any of these things. I'm going to stop there, and I'll come back in a second. Stop sharing, and I'm going to end recording, and I'll see you in class. Bye.